at over 1,400 degrees Celsius inside giant cylindrical furnaces. Then, a tiny seed crystal is dipped into the molten pool. Slowly, over many hours, it is pulled upward, rotating gently, growing a perfect cylinder of pure silicon called an ingot. This ingot can weigh over 100 kilograms, and it contains a raw material for thousands of future AI chips. One single chip, less than 1 inch wide, worth more than its weight in gold. This is not science fiction. This is happening right now, at a scale most people cannot imagine. NVIDIA's AI chips are powering everything from self-driving cars to military satellites. And the factory that makes them is unlike anything ever built by human hands. Here is a question almost nobody asks. If AI is the future of the world, then what builds AI? The answer is a chip. And the answer to what builds that chip is something even more extraordinary. A billion-dollar robotic factory so advanced, so precise, so automated, that even a single human breath could destroy everything inside it. Stay with us. This is a real story. NVIDIA, a name that started in a small California office in 1993. Today, it is one of the most valuable companies on the planet. Its market cap has crossed $1 trillion. And the reason is simple. NVIDIA makes the chips that make AI think. Without NVIDIA's hardware, the artificial intelligence revolution stops cold. That is how critical this company has become. But NVIDIA does not manufacture its own chips. It designs them with thousands of engineers. Then it sends those designs to the most advanced semiconductor fabrication plants on Earth. These facilities are called fabs. They are built by TSMC, Taiwan's semiconductor manufacturing company. And what happens inside them is the most complex manufacturing process ever created by human civilization. Why does this matter to you? Because every AI model you use, every smart device you touch, every autonomous vehicle on your roads, all of it depends on what happens inside these factories. The United States is now investing hundreds of billions of dollars to bring this manufacturing power to American soil. The stakes have never been higher, and the story has never been more important. It begins with sand. Ordinary silicon dioxide, the same material in beach sand, is the foundation of every chip on Earth. But this is no ordinary process. That raw silicon is purified to an astonishing 99.9999999% purity. 99's a purity. Even one stray atom of contamination can destroy a chip worth thousands of dollars. The journey from sand to supercomputer starts here. The purified silicon is melted at over 1,400 degrees Celsius inside giant cylindrical furnaces. Then, a tiny seed crystal is dipped into the molten pool. Slowly, over many hours, it is pulled upward, rotating gently, growing a perfect cylinder of pure silicon called an ingot. This ingot can weigh over 100 kilograms, and it contains a raw material for thousands of future AI chips. That silicon ingot is then sliced by diamond wire saws into wafers, thin circular discs no thicker than a credit card. Each wafer is polished to an atomic level smoothness. Robotic arms handle them with a grip so gentle, so precise, that no human hand could ever match it. One scratch, one particle of dust, and that wafer, worth tens of thousands of dollars, is gone. Now we enter the clean room, and this is where the world changes. This facility maintains air that is 10,000 times cleaner than the air outside. Workers wear full-body suits called bunny suits. They look like astronauts. They move slowly. They speak in whispers. Because here inside these walls, the rules of the ordinary world simply do not apply. Everything is controlled. Everything is perfect. The heart of the clean room is a machine called the EUV lithography system. EUV stands for extreme ultraviolet. This machine costs $350 million. There are fewer than 200 of them in the entire world. ASML, the Dutch company that builds them, is the only company on Earth that can make them. Without this single machine, NVIDIA's most advanced chips cannot exist. Here is how the EUV machine works. It fires a laser 50,000 times per second at tiny droplets of molten tin. That creates a burst of extreme ultraviolet light. That light is then bounced off a series of mirrors so flat they would span the size of Germany, but deviate less than the width of an atom. This light is then used to print circuit patterns onto the silicon wafer, patterns measured in nanometers. Here is how the EUV machine works. It fires a laser 50,000 times per second at tiny droplets of molten tin. That creates a burst of extreme ultraviolet light. That light is then bounced off a series of mirrors so flat they would span the size of Germany, but deviate less than the width of an atom. This light is then used to print circuit patterns onto the silicon wafer, patterns measured in nanometers. The lithography process happens in multiple layers, like printing a newspaper, but with 100 layers stacked on top of each other, each layer precisely aligned to the ones below. Between each layer, robotic systems deposit materials, etch patterns, and wash the wafer in ultra-pure chemicals. Every step is timed to the millisecond. Every movement is controlled by AI systems monitoring thousands of variables simultaneously. And here is something extraordinary. The robots doing this work never get tired. They never lose focus. They never touch the wafers with anything that could contaminate them. Robotic arms made of ceramic and stainless steel glide through the cleanroom on magnetic rails. They move wafers from station to station in sealed pods called FUPs, front-opening unified pods. Nothing human touches a wafer at this stage. Nothing. Let us pause here, because right now, as you're watching this, thousands of these processes are happening in parallel. On a single production line, every second, machines are depositing atoms, etching circuits, measuring results, and making adjustments. A modern fab processes hundreds of wafers per day. Each wafer can produce hundreds of chips. The scale is almost impossible to wrap your mind around. But precision requires more than machines. It requires intelligence. And this is where NVIDIA's own AI becomes deeply ironic. The systems that control these factories are powered by AI chips. To make more AI chips, you need AI chips already working. It is a cycle, a loop of machine intelligence building more machine intelligence. The factory is feeding itself, and it is accelerating. Deep inside the fab, there are machines called chemical-mechanical planarization systems. Sounds complicated, but think of it like polishing a surface, so flat it reflects like a mirror. After every single layer of the chip is added, robotic arms apply pressure down to a fraction of a gram. Sensors measure the surface 10,000 times per second. If anything deviates even slightly, the system corrects itself. Automatically, instantly. Now we move to ion implantation. This is where atoms are literally shot into silicon at high velocity using a particle accelerator. Not a full-size particle accelerator, but a miniaturized version, the size of a car. These ions change the electrical properties of the silicon at a quantum level. This is how transistors are given their ability to switch on and off billions of times per second. Think about that for a moment. Billions of switches, turning on and off, billions of times, every single second, inside a chip smaller than your thumbnail. That is what makes AI possible. That is what makes your phone smart. That is what makes self-driving cars see the road. Every calculation in the modern digital world comes back to this. Tiny switches in silicon, firing at the speed of electricity. As the wafer progresses through the factory, it passes through over 1,000 individual process steps, more than 1,000, spread across weeks of continuous processing. During that time, sensors collect millions of data points. AI systems analyze every measurement in real time. If a wafer shows signs of problem, a deviation too small for any human eye to see, the system flags it. The wafer is pulled, inspected, or discarded. The inspection systems inside a modern fab are astonishing. Electron microscopes scan wafer surfaces at atomic resolution. Machine vision cameras capture images of circuit patterns and compare them to the perfect digital blueprint. Any defect, even a single misplaced atom in a critical location, triggers an automated response. The system does not wait for a human. It acts every time, without fail. By now you might be wondering, where are the humans? They are there, but their role is very different from what most people imagine. Human engineers do not touch the wafers. They do not operate the machines manually. They design processes, analyze data, solve novel problems, and oversee systems that run themselves. In a modern fab, one engineer can supervise hundreds of robots working in parallel. That is the new reality of manufacturing. Let us talk about the scale of investment. Building one advanced semiconductor fab costs between $15 and $20 billion. That is more than many countries spend on their entire defense budget in a year. The machines inside alone cost hundreds of millions each. The clean room infrastructure, its air filtration, its vibration isolation, its ultra-pure water systems, is itself a marvel of engineering worth billions. Ultra-pure water. You might not think about water when you think about chip manufacturing, but modern fab uses millions of gallons of ultra-pure water every single day. This water is purified beyond what any human could drink safely, so clean that it actually leaches minerals out of your body. It is used to rinse wafers between process steps. One contaminant in that water, and entire batches of chips are destroyed. The chemicals used in chip manufacturing are equally extraordinary. Hundreds of different compounds, acids, gases, solvents, each managed by automated systems. Robotic dispensing units measure these chemicals in quantities smaller than a drop of rain. The entire chemical supply chain within a fab is controlled by sensors and AI. No human manually measures or pours anything. The margin for error is effectively zero. After weeks of processing, the wafer finally reaches the testing stage. And this is where we find out which chips survived. Automated probe stations lower microscopic needles onto each chip simultaneously and run thousands of electrical tests in milliseconds. Chips that pass are marked. Chips that fail are discarded. The yield, the percentage of working chips per wafer, is one of the most closely guarded secrets in the semiconductor industry. For NVIDIA's most advanced chips, yield could be as low as 50% on initial production runs, sometimes lower. Half the chips on a wafer might fail. But here's the key. Even a 50% yield on a wafer containing chips worth thousands of dollars each is still enormously profitable. And as the process matures, yield improves. Engineers study every failure, every defect pattern, and they optimize relentlessly. The surviving chips are then cut from the wafer, a process called dicing, using laser systems accurate to within micrometers. Each individual chip, now called a die, is picked up by robotic vacuum systems and placed into packaging. This packaging is not just a protective shell. It is an advanced substrate containing thousands of microscopic connections, a miniature circuit board in itself. And this packaging process is just as complex as the chip itself. NVIDIA's most advanced chips, like the H100 and the new Blackwell architecture, use a technology called chaplet packaging. Multiple dies are connected together on a single package using thousands of tiny copper bumps called micro bumps. The alignment precision required is measured in microns. Robotic systems perform this assembly at room temperature, then apply controlled heat and pressure to permanently bond the chips together. It is like assembling a city out of grains of sand. Now, let us go deeper, because the real intelligence in these factories is not in the robots. It is in the software. Every machine in a modern fab is connected to a central data system. Thousands of sensors stream live data every second. AI models analyze process variations, predict equipment failures, optimize chemical recipes, and adjust parameters in real time. The factory is not just automated, it is alive with machine intelligence. Machine vision is one of the most critical technologies in the fab. Cameras capable of imaging individual atoms scan every wafer at multiple stages. These systems use deep learning models trained on millions of defect images. They can identify a defect pattern in milliseconds, classify it, trace it back to a specific machine, and alert engineers before an entire batch is affected. This is AI protecting the process of making AI. The data control rooms inside these facilities look like something from a space agency. Walls of screens displaying real-time metrics from every machine on the floor. Process engineers monitor trends, spot anomalies, and communicate with robotic systems remotely. Some facilities use augmented reality headsets that overlay machine data directly onto physical equipment. Engineers can see a machine's internal state without opening a single panel. Smart sensors are embedded everywhere. Inside vacuum chambers, inside chemical tanks, inside robotic joints. They measure temperature, pressure, particle count, vibration levels, and chemical concentrations, All of this data feeds into predictive maintenance systems. Instead of waiting for a machine to break down, the AI predicts failure days or weeks in advance. Maintenance is scheduled. Downtime is minimized. Production never stops. Predictive maintenance alone saves semiconductor fabs hundreds of millions of dollars per year. An unplanned equipment failure in a fab can destroy an entire batch of wafers worth millions of dollars in minutes. But with AI power prediction, that almost never happens. The machine tells you it is going to fail before it does. It is the difference between a small repair and a catastrophic shutdown. Energy is another hidden dimension of these factories. A single advanced fab consumes as much electricity as a small city, hundreds of megawatts of continuous power. To manage this, smart energy systems distribute and monitor power consumption across thousands of machines. Some fabs are beginning to integrate renewable energy sources and on-site power storage. The goal is not just efficiency, it is resilience. Because if the power goes out, the consequences are catastrophic. The speed metrics inside a modern fab are staggering. Wafers move through facility on automated conveyor systems at precisely controlled speeds. Robotic delivery systems respond to requests in seconds. Process times are tracked to the millisecond. The entire production schedule is managed by AI systems that continuously optimize the flow of hundreds of wafers simultaneously, like a three-dimensional chess game played at machine speed, never stopping. Even the air in these facilities is smart. HEPA and ULPA filtration systems remove particles as small as 0.1 microns from every cubic meter of air. Airflow is carefully engineered so that contaminated air always flows away from the wafers. Pressure differentials between rooms ensure clean air flows outward, not inward. Particle counters monitor the air continuously. If contamination rises above a threshold, the system responds automatically. Every breath of clean air is manufactured. The vibration isolation in a modern fab is another engineering marvel. EUV machines and electron microscopes are so sensitive that a truck passing on a road outside could blur a circuit pattern and ruin a wafer. Fabs are built on enormous concrete foundations with active vibration cancellation systems, essentially noise-canceling technology for the ground itself. Sensors detect incoming vibrations and generate counter vibrations to neutralize them. The machines float on controlled stillness. After packaging, every NVIDIA chip goes through final system-level testing. Complete GPU boards are assembled and run through intense computational stress tests. AI software pushes every circuit to its operational limits. Temperature, power consumption, and processing speed are all verified against specification. Only chips that pass every test ship to customers. The ones that partially fail are reprogrammed and sold in lower-tier products. Nothing is wasted. Every silicon die finds its purpose. Now comes the question that matters most. What does all of this mean for jobs? The answer is complicated. Automation has eliminated thousands of manual manufacturing roles, but it has created entirely new categories of work. Process engineers, data scientists, AI systems operators, robotics technicians. The jobs are fewer, but they are higher skilled, higher paid, and more technically demanding than anything that came before them. The United States government is making a historic bet. The CHIPS Act allocates over $52 billion to bring semiconductor manufacturing back to American soil. Intel, TSMC, and Samsung are all building advanced fabs in the United States. The goal is strategic independence, to ensure that America's most critical technology infrastructure is not dependent on factories located in geopolitical flashpoints on the other side of the world. Because here is the uncomfortable truth. The most advanced chips in the world are currently made in Taiwan, and Taiwan sits in one of the most geopolitically sensitive regions on the planet. A disruption to chip supply, from conflict, from natural disaster, from political tension, would send shockwaves through every sector of the global economy. Cars, hospitals, military systems, financial networks, all of them would be affected. This is why chips have become a matter of national security. The military applications of AI chips are already reshaping defense strategy. Autonomous drones guided by NVIDIA-class processors. AI systems analyzing satellite imagery in real time. predictive logistics platforms that keep supply chains moving during conflict. The chips coming out of these factories are not just commercial products. They are strategic assets. And every major military power on Earth knows it. The race is not just for market share. It is for technological supremacy. The electric vehicle revolution also runs through these factories. Modern EVs require sophisticated AI chips for battery management, autonomous driving systems, and real-time navigation. As EV adoption accelerates, demand for advanced semiconductors grows with it. The same chips powering AI data centers are evolving into versions that power the vehicles of the future. The factory you are learning about today is building the engine of an entirely new transportation era. And then there is the ethical dimension. As these factories become more automated, as AI systems gain more control over critical infrastructure, questions arise. Who is responsible when an AI system fails? Who owns the economic gains from automation? How do we ensure that the communities displaced by this technological shift are not simply left behind? These are not distant philosophical questions. They are happening right now, and they demand real answers. Step back for a moment. Think about what you have just learned. From a grain of sand to a wafer of pure silicon, through 1,000 steps of robotic precision, guided by artificial intelligence. Inside rooms cleaner than any place on Earth, a chip emerges. A chip that will think, that will reason, that will drive cars, diagnose diseases, create art, and translate every language spoken by humanity. All from sand, all from light, all from human ingenuity pushed to its absolute limit. We are living through the greatest technological acceleration in human history, and most people do not see it. They use AI every day and never wonder what makes it possible. But now you know, behind every prompt you type, behind every image that AI generates, behind every decision a machine makes, there's a factory, there's a robot, there's a chip built with precision that took humanity decades to achieve and seconds to run. And here is what keeps engineers and scientists awake at night. We are approaching the physical limits of silicon. Transistors cannot shrink forever. Quantum effects start to interfere. Electrons begin to tunnel through barriers they should not cross. The next frontier is already being explored. Quantum chips, neuromorphic processors, photonic computing. What you have seen today is not the end of the story. It is only the end of this chapter. The next one has already begun. The factory that builds the future is running right now. Robots are working. Lasers are firing. Silicon is becoming intelligence. And the world is being remade, one chip at a time. If this story opened your mind, do one thing right now. Hit that subscribe button, because we're just getting started. Drop a comment below. Tell us which part surprised you the most. And share this with someone who needs to understand what is really powering our world. The future is being built. Are you watching?